This is the last of the material for exam 1. We're going to cover blood vessels, circulation, and cardiovascular physiology. We have 5 classes of blood vessels, and I have mentioned the majority of them already, but we're going to go into a little bit more detail. Arteries, arterioles, capillaries, venules, and veins. And they're in this order for a reason, because this is the way that they occur. Arteries carry blood away from the heart. They are the largest vessels that do. They branch and eventually will become arterioles, which is the smallest form of an artery. Arterioles become smaller and they become capillaries. These are the smallest of blood vessels, and they are neither considered arteries or veins. They are in a group by themselves. And these are also called the exchange vessels, and this is for exchange between blood and interstitial fluid. On the other side of a capillary bed, you will see venules. These are the smallest of the veins, and they are collecting blood from the capillaries that is full of carbon dioxide waste and excess nutrients and devoid of oxygen. Venules eventually become the largest of the blood vessels are the aorta and the pulmonary trunk. We know that the pulmonary trunk is going to carry blood from the right ventricle to the pulmonary circulation. So it goes from the right ventricle to the pulmonary trunk to the right and left pulmonary arteries. It goes down to the lungs, and then the right and left pulmonary veins are going to bring the blood from the lungs back to the heart to the left atrium. The aorta carries the blood from the left ventricle and divides and allows for blood to enter the pulmonary circulation. The smallest of the blood vessels are the capillaries. When you look at vessels, either veins or arteries, there is the inner, the middle, and the external layers. The tunica intima is the innermost layer. It is an endothelial lining. It has connective tissue as well. If you look at the arteries compared to the veins, in arteries, there are also elastic fibers. The tunica intima in arteries is ruffled. As you can see in veins, it is actually straight. The middle layer for the tunica media, it's known as the middle layer. We have concentric sheets of smooth muscle. It's also found in loose connective tissue, and it's going to bind the inner layer to the outer layer. There is an elastic membrane that separates the tunica media from the tunica externa. The tunica externa is the outer layer, and it has a connective tissue sheath. It's going to anchor the vessel to whatever is around it, to adjacent tissues. If it's in an artery, it has collagen and elastic fibers. If it's in a vein, it has smooth muscle and elastic fibers. So you can see that there are differences between the arteries and the veins. Notice that arteries have much more elastic fiber. Again, to compare arteries and veins, you see on the upper right, we have a vein. On the lower left, we have an artery. You do find them side by side. Arteries have thicker walls and they have much higher blood pressure. A collapsed artery still has a round lumen. A vein has a large flat lumen. You can see the shape of the lumens in the picture. A vein lining can contract, artery linings don't. An artery lining has a fold. Remember I said it's roughly. There's more elastic in arteries. Veins have valves, arteries do not. Veins are bigger, arteries are smaller. Veins have thinner walls. They carry. Here is a visual comparison of arteries and veins, and we're going to go through each different category of arteries, then capillaries, and then veins. As we've already said, arteries are more elastic. because they need to absorb greater pressure. They can change diameter, that's controlled by your autonomic nervous system, so they have contractibility. They have vasoconstriction, and that's contraction of the smooth muscle by the autonomic nervous system. Vasodilation allows for the lumen to become larger. And then as we go from the heart to capillaries, arteries change from elastic to muscular to arterioles. The elastic arteries are large. They're also known as the conducting arteries. The pulmonary trunk and aorta are great examples of these arteries. They even out the pulse force because there is a tremendous amount of pressure, so thus a greater pulse force. The muscular arteries are smaller. Elastic arteries divide and become muscular arteries. Sometimes they're called distribution arteries so that they can distribute the oxygenated blood throughout the systemic circuit. They're medium size. Like I said, it's the majority of arteries, and it has many smooth muscle cells. Arterioles are the smallest of arteries, and they have little to no tunica externa. They may have an incomplete tunica media, so they're very, very thin walled, but you can see. So when you look at the diameter, in the muscular arteries and in the arterioles, they're going to change based on what the sympathetic nervous system or the endocrine system tells them to do. If the amount of oxygen is low, then dilation is going to occur to allow more blood to flow. If the amount of oxygen is low, then you're going to have more pressure needed. Capillaries are the smallest vessels, and they have incredibly thin walls. Capillary networks are throughout all of your tissues. As we've stated repeatedly, this is where you have diffusion occurring and oxygenation and nutrient passage through the tissues to your cells, so that you can produce ATP and run the cell and make the proteins that you need to. All of that is necessary so that you can be in homeostasis. So we know that we're going to have diffusion between the blood and interstitial fluid. It's a two-way exchange. You're picking things up and kicking things out. It is an endothelial tube. Has a very thin basal lamina. There's no tunica externa, no tunica media, and the diameter for the majority is close to that of a red blood cell, or approximately 8 micrometers, but some of them are tiny, like 4 micrometers. So there's a few different types of capillaries that we're going to talk about. The first one is continuous. They're called continuous because they have this complete endothelial lining. So you can see in this image, you have the endothelial cells with, you can see the nuclei. They are a single cell layer thick. They have incomplete tight junctions. You can find continuous capillaries with these incomplete tight junctions everywhere, but within your central nervous system. You need to have continuous capillaries that are specialized in your central nervous system, because your brain is going to be isolated from chemicals. So remember the blood-brain barrier, and they have tight junctions. Continuous capillaries are found everywhere except in your epithelia and in your cartilage. They are specific in that they allow diffusion of water, small solutes, lipid-soluble materials, but they block blood cells and plasma proteins, right? Because you don't want the ability for blood to leave your capillaries. That would kind of negate the reason for your capillaries. Fenestrated capillaries are the second type of capillary that we are going to discuss. They have an endothelial lining, again, a single cell layer thick, and they have tight junctions. However, they have what are called fenestrations or pores, and you can see the fenestrations here and here. Here's the boundary between a cell, right? They have tight junctions, but they have pores within the cells. So this allows for a rapid exchange between the interstitial fluid and plasma. So if we're talking about the small intestine, endocrine glands, or kidneys, it is necessary to have this rapid exchange of water and larger solutes. So these are clearly more permeable than continuous capillaries because they do. Sinusoids are the capillary that are least common. They look a bit like a fenestrated capillary. You find them in your liver, spleen, bone marrow, endocrine organs, a lot of your reticulated organs or reticular organs, you can find them. So the gaps that you find in sinusoids is that they actually have spaces between the endothelial cells. And this allows for this free exchange of water and large plasma proteins. The exchange is slower, but there's also more exchange opportunities. And you would think that this would be unsafe. However, we evolved to have phagocytes that monitor the blood at sinusoids so that you don't let the bad guys in, right? This image shows a great representation of all three types of capillaries. Regardless of the type of capillary we're talking about, they all will be active in capillary networks. So you may have heard of capillary beds. Someone's done damage to a capillary bed. Maybe they smashed their finger or something like that. These capillary beds or capillary plexuses are going to connect one of the tiniest arteries and one of the tiniest veins, so an arteriole and a venule. And you can see that in this picture where there is an arterial vessel on the left side and a venous vessel on the right side. So looking at this image, you can see some different structures through here. One of them is a thoroughfare channel. So this is called a thoroughfare channel. So this is a direct connection in the capillary bed between the artery and the vein. And this is going to be controlled by smooth muscle segments. And that's what you're seeing all through here is that we've got smooth muscle cells. We also have collaterals. So whenever you have two, these are collateral arteries. Whenever you have two collateral arteries coming together, they come together at an arteriole. It allows for circulation if one of the one of the arteries is blocked. An arterial anastomosis is when you have two collateral arteries, like here and here, that come together and they fuse in case one is blocked. An arterial venous anastomosis is what you see right here, and that is a direct connection, again, between the arterioles and the venules, but they're straight up bypassing this capillary bed in case there is an issue here. I'm going to get rid of some of this. All right. I also want you to notice that we have some dotted lines and we have some non-dotted lines. Dotted lines means it could happen. Straight lines mean it is happening, all right? So I didn't get rid of one of these. All right, here you can see it's going to A capillary sphincter is going to guard the entrance to each capillary. And these sphincters open and close, and they cause the blood to flow in pulses. So this is what I want you to notice with these dotted lines. These dotted lines are indicating that we're going to have vasomotion. So this ensures that you're going to have blood flowing and feeding your tissues no matter what is going on, even if you're at rest. So it's changing the routes to be constantly changed. That's the reason why there's dotted lines here. Could be going here, could be going here, could be going up here, right? So this vasomotion allows for us to have this consistent distribution of oxygen to our tissues. I also want you to notice the change in color. Remember, I told you oxygenated blood is red, deoxygenated is blue. And look what's happening as the blood goes through the capillary. It's changing color. With your veins, you have venules that are very small veins, which are connected to the capillaries. You have medium-sized veins that are the next larger veins. They have a very thin tunica media and a few muscle cells. They're small. They can be 2 to 9 micrometers in diameter, right? So, I mean, we're looking at something that's really, really small. And then those large veins are going to have 3 layers. They have a thick tunica externa. So you can see that in this image up here where you have a thick tunica externa, the tunica media, and then with veins, we have valves, which are so incredibly necessary. Remember, I told you earlier on, I'd like for you to think about one red blood cell as it is making its way through your body from the time it is ejected from your heart through your aorta to the time it makes it all the way back up to your right atrium. So when you think about that, I want you to think about that red blood cell when it's in your big toe. And I want you to think about what it's doing while you're standing or sitting, right? Unless you're laying flat on your back or you have your feet straight up in the air, that red blood cell is not going to be under a tremendous amount of pressure. How does it make its way back up? Well, we have valves in our veins, and it's folds of the tunica intima. And so these valves prevent backflow. So if you look at this image, you have blood veins that are in your lower leg. And here you can see that we have not just valves, but we also have muscles. Those muscles are going to contract. And when that happens, it's going to push the blood that's in the vein up so that it can continue on through the systemic system. And you'll notice it's almost like a semilunar valve, that this valve is almost like a semilunar valve in that when we have pressure here and here, the blood does not backflow down here. It actually closes, right? So with pressure, this one opens and this one closes. So this compression is going to push blood toward the heart. And so this is the theory behind compression hose or compression socks. Because you have consistent pressure, it is going to help with your blood flow, and it keeps blood from pooling in your lower extremities. If you have problems with valves or with blood flow, it can lead to varicose veins and hemorrhoids. So hemorrhoids can occur because someone is straining to defecate. So it's pushing a lot of blood into those tissues, and the valves will actually help the blood come back. But if you damage the valves, then you can have hemorrhoids from that. So there's a few different things that you can read in those links in regard to varicose veins. All right, how is your blood distributed? Well, if you look in your systemic system, which is this light blue right here, then you can see that the majority of blood, 64%, is in your systemic system at any one time. Only 9% is in your pulmonary system, 7% is in your heart, 13% is in your systemic arterial system, and 7% is in your systemic capillaries. What I should have said earlier, 64% is in your systemic venous system. So when you break it down to the systemic arterial system, you can see how much is in each type of artery. But also when you look at the systemic venous system in the blue, think about where, let's look at some cardiovascular physiology. So what allows for this capillary, this blood flow capillary blood flow in our peripheral tissues? Well, whatever is in our capillaries has to equal cardiac output. And so this is going to be determined by blood pressure and resistance in your cardiovascular system. Okay? So when we measure blood pressure, as we talked about before, we're measuring arterial pressure, and that's done in millimeters of mercury. We also have to understand our capillary hydrostatic pressure, which is our CHP. That's the pressure within our capillary beds. Then we have venous pressure, the pressure within our venous system. But if we look overall, we're looking at circulatory pressure. That is the change, or delta P, change in pressure across your systemic circuit. And that's about 100 millimeters of mercury. From the time blood leaves the heart and goes into the aorta to the time it returns to the heart, we're looking at a decrease of about 100 millimeters of mercury. Don't worry, I'm going to show you how this works. So in order for us to have this capillary blood flow and to have venous return, our circulatory pressure has to overcome peripheral resistance. So peripheral resistance means the resistance that comes because of the vessel. It is what is in the periphery around the blood. And resistance, R, means the resistance of the entire cardiovascular system. So what is going to affect this blood flow and cardiovascular regulation? You have your nervous system and you have hormones that are going to regulate cardiac output, venous pressure, and peripheral resistance. Cardiac output affects arterial pressure, which also affects peripheral resistance, which also affects capillary pressure. Vascular resistance is the resistance of the blood vessels, and that's this friction that's between the vessel and the blood. And it depends on the length and vessel diameter. And I want you to think about turning on your outside faucet and you have a hose attached. If you have a hose that's 10 feet long and you turn the faucet on full strength, it's going to come out at X pressure. If you have a hose that's 100 feet long and you turn the faucet on full strength, it's going to come out with less pressure just because of the distance. Now, the good thing is adult vessel length is consistent, so we can make educated guesses about vascular resistance for adults. So the length is constant, but the diameter is going to change based on dilation and constriction. So resistance is going to increase as the diameter decreases. And what happens as we go from arteries to arterioles to capillaries? We're decreasing the vessel diameter. Okay, just look at the picture. When you look at this picture, we're looking at millimeters of mercury here, right? And we're looking at from the aorta all the way back to the vena cava, right? When blood is released from the left ventricle, we have extremely high pressure that goes up just a bit, tiny amount, when it gets to the elastic arteries, right? So we're looking when it's in the aorta, gets to the larger arteries, but as we get to the muscular arteries, it begins to decrease and decrease and decrease and decrease. Now we're at the arterioles. Okay, look at your blood pressure when it hits a capillary, right? It's about, I don't know, 25. That's when it enters the capillary. Look what happens by the time it leaves the capillary. 18, 15, let's say 15, makes the math easy. If this is 25 and this is 15, you've lost 10 millimeters of mercury in your capillaries. Then it hits the venules, right? And you have to push this up these veins and get it back to your heart with this ever decreasing pressure. And then by the time it gets to the vena cava, it's essentially passively draining into the right atrium, right? This is incredibly important to understand when we say arteries undergo tremendous pressure. Veins, not so much. Why do veins look different than arteries? I think you can see why here. Okay, so let's look at a few different things about pressure. Systolic pressure, peak arterial pressure during ventricular systole, right? That's when the blood is being pushed out of the heart. Diastolic pressure is the minimum arterial pressure. So what do we say? 110, 120 over 80, that's a okay blood pressure, good blood pressure, right? So that is your systolic measure, and this is your diastolic pressure. Hypertension is defined as anything that's greater than 140 over 90. Hypotension is abnormally low blood pressure. Your mean arterial pressure and pulse pressure are going to decrease with the distance from the heart. Okay, that only makes sense as you can see the pressures are actively decreasing. And this pressure is going to decrease as it overcomes the friction. Once we get to the venous side, the amount of blood that arrives in the right atrium each minute is going to be determined by that venous pressure. And there's low venous resistance. Remember what the lumens look like? They're huge, right? So you've got this minimal venous resistance. And this venous return has got to be helped by muscle contractions and the respiratory pump. And that respiratory pump, right? So here's a good image of your respiratory pump. This is what's happening in your thoracic cavity. When you inhale, take a breath in, you expand your thoracic cavity, and air is going to be pulled into your lungs, and that also pulls blood into your inferior vena cava and your right atrium. As you exhale, right, you're contracting your thoracic cavity, it pushes venous blood into the right atrium again. So here you can see what your respiratory pump is doing in this. All right, so capillary exchange is huge. We have talked about capillary exchange in A&P1, and I keep referring to it here. And this is another process that you're going to need to know. This is movement across the capillary walls, whether you're moving something into the capillary or out of the capillary, and this is going to occur by diffusion, filtration, or reabsorption. So remember, diffusion is the movement of ions or molecules from a concentration of high concentration to an area of low concentration. How can this happen? Well, you can move water ions, small molecules, glucose maybe, between cells at junctions, or maybe through a fenestrated capillary. Some ions go through channels. Remember, we talked about this, about sodium and potassium channels and calcium channels in cell membranes. If it's large and water soluble, it can go through fenestrated capillaries. If it's lipid solubles, O2 and oxygen, it just diffuses straight through the cell membrane. All right, so let's look at a little bit of capillary filtration. So we're removing large solutes through a porous membrane. So with this, we're forcing water and small solutes through a capillary wall, and the larger substances are being left inside the blood vessel. And you can see that in the top picture. Glucose is able to make its way through into the interstitial fluid, but the blood proteins are too big and they can't actually go through those pores. If we're talking about reabsorption, this is the result of osmosis. Remember, we have water moving, so that allows for a greater concentration to occur in the area that the water moved out of. We also have blood colloid osmotic pressure. Colloids are large substances. So if it's a blood protein, if they're too big, that is going to create a pressure issue because they cannot cross the capillary walls. And hydrostatic pressure is going to force water out of a solution. Osmotic pressure forces water into a solution. So it's this osmotic pressure and the hydrostatic pressure that is going to control filtration and reabsorption. When we look at capillary exchange, I'd like for you to look at this picture and look where the colors change. This is called the arterial end, and this is called the venous end of the capillary. And I know there's a lot of business going on here and a lot of business going on here, but I want you to just very easily understand that on the arterial end, we have net filtration, so we're pushing items out. On the venous end, we have net reabsorption, and we're pulling things in. And why can we do that? We can do that because the net filtration pressure on the arterial end is 10 millimeters of mercury, right? So we push things out. The net filtration pressure on the venous end is -9, right? So we can pull things in. That's the big take home here. So we're pushing out water and solutes into the interstitial fluid, right? On the venous end, we have a low net filtration pressure, and so this allows for water and solutes to be pulled from the interstitial fluid into the capillary, right? Also remember what's going on here is that we are diffusing out oxygen, so we're going from oxygenated blood slowly to deoxygenated. So at the arterial end, you have capillary fluid that's moving out of the capillary and into the interstitial fluid. At the venous end, you have capillary fluid that moves into the capillary and out of the interstitial fluid. This transition point is actually closer to the venous end. It's not exactly in the center. It's closer over here. In that we have capillaries that filter more than they absorb. If there's excess fluid, it's going to enter the lymphatic system that you can see right here. So we recycle our fluid, and the water is going to just move back out into the capillaries, back into the bloodstream, and this is going to happen. Here are some good images of one of the things I just talked about. This is a simpler diagram with net filtration pressure. This one says 8 millimeters of mercury. I'm not really stuck on that you know the numbers. I just need for you to know that this allows for filtration to occur because it's a positive number, and that this allows for reabsorption to occur because it is a negative number. And that this is positive number is on the capillary end and the negative number is on the venous end. This is also a good image of how with every vessel that you also have lymph vessels that are associated with it. So this yellow indicates lymph vessels, and it's picking up additional fluid. So we have this blood and lymph cycle that allows for constant communication between the interstitial fluid and your plasma. It allows for distribution of nutrients and hormones and dissolved gases. It also allows for proteins that can't cross capillary walls to be transported in insoluble lipids, and it allows for the flushing of toxins. If a person is hemorrhaging, you have reduced capillary hydrostatic pressure and net filtration pressure, and that means that you're going to increase the reabsorption of interstitial fluid. Because you're hemorrhaging, you're going to resorb as much interstitial fluid as you can. If you're dehydrated, that increases your blood colloid osmotic pressure, and it's going to also accelerate reabsorption. If you have edema, this is an increase in your capillary hydrostatic pressure or your blood colloid osmotic pressure, and it moves fluid out of the blood and builds up in your tissues.